Alright, hello class. Today we are looking at section 5.3, which is on what is called the Fundamental Theorem of Calculus. So, it's probably no surprise that this is a very important topic in this class. Basically, if you're ever learning any kind of math, if you're ever sitting in a math class and somebody starts telling you about the fundamental theorem of that subject, chances are it's pretty damn important. The fundamental theorem of calculus is the big theorem that relates derivatives to integrals, and the way that we already know how they should be related, but it also gives us a way to calculate definite integrals, right? It gives us a way to calculate this thing here, the definite integral from a to b of f of x dx, which, if you remember, was this really crazy infinite sum, right? Where k is going from 0 to infinity, f of x k delta x. Right, which here is an infinite sum. I mean, we're summing up an infinite number of things, and we're multiplying by this delta x, which is shrinking down to 0 at the same time. The fundamental theorem of calculus gives us a very, very, very quick way to actually calculate this thing here. Okay, so let's just start off by looking at the statement of the theorem, and then we'll look at some examples dealing with it. Okay, here's the fundamental theorem of calculus part 1. So the fundamental theorem of calculus comes in two parts. The part 1 is important. I mean, it's really integral to the study of calculus, of course, but it's not one we'll be using a lot as far as examples go, mainly because it should be pretty clear, I think. Basically, if we have f is continuous on the closed interval a to b, and if we have this area function a of x, which you saw in one of your worksheets, so if a of x, the definite integral from a to little a to x of f of t dt, then we have that as continuous on a to b and differentiable on the open interval a to b. And specifically, a of x satisfies this thing here, that a prime of x is equal to f of x. What this is really saying here, that provided f of x is continuous on the closed interval a to b, we have this thing here, that a prime of x, in other words, when we take the derivative with respect to x, of the integral from a to x of f of t dt, we just get out f of x. In other words, the derivative cancels out the integral. Okay, that should make sense, right? If you take the integral and then take the derivative, you should get right back to where you started from, right? That goes hand in hand with this little diagram I drew at the very beginning of chapter 5, that, you know, the derivative takes us to f prime, whereas the integral takes us to f. So if we say take the derivative of the integral, we should just get right back to where we started from. That's sort of the idea of what this is saying. But as far as problems dealing with this, you probably won't see very many, but if you do, say you have this integral here, maybe 2 to x of cosine t dt, and you're taking the derivative of that. Right, it's simply just cosine x. Okay, the derivative and the integral all cancel, and you put the x into the variable there. Okay, replace t with x, and that's pretty much it. Okay, so that's the first part of the fundamental theorem of calculus. Basically, it tells us that the derivative and the integral cancel, at least in this order. Okay, let's look at the part 2 of the fundamental theorem of calculus. Okay, here we go. the fundamental theorem of calculus, part 2. If f of x is continuous on a to b, okay, and capital F of x is any antiderivative, right? Any, and that's an important part there, of f of x. Then the definite integral from a to b of f of x dx is simply capital F of b minus capital F of a. All right. This is a huge deal because if you remember, this thing right here is a very complicated sum. Right? That's an infinite sum. Right? You're summing up every f of x from a to b. Right? F of a, you know, plus 0.00001 all the way up to b. Every point between them. And you're multiplying by delta x, which goes to 0 at dx. Okay? That is an extremely difficult thing to do by hand. In fact, impossible. The only thing you could do is approximate it somehow. Okay? But what the fundamental theorem of calculus says is that, hey, this is actually very simple to do. This super complicated thing, probably the most complicated thing you may have ever seen in a math class before, that infinite series, or the infinite sum, okay? All you have to do is plug in b, plug in a into a function and subtract. Provided you can find that capital F. And what is the capital F? Simply any antiderivative of little f. That's it. Okay? So that is why the antiderivative uses this notation here with the integral sign, without the limits, of course. It's because it's so closely related to this definite integral, this sum. That symbol came from S for sum, and we get that, or we call the antiderivative using the same notation because this is the antiderivative right here. We're just plugging in values. Okay? An equivalent way to write this, and this is where it really kind of compares or gets the derivative and the integral working together. Equivalently, you can say that if the derivative f prime of x is continuous on a to b, then the definite integral from a to b of f prime of x dx is f of b minus f of a. Okay. And if you wanted to write this in terms of, say, velocities and positions, you could do that. And we'll do that in a second. But, I mean, as we can see here, this relates the derivative and the integral. So essentially what we're saying here is that when you integrate the derivative, you get back to a form of that original function. So it's not as clean as this direction, right? When you take the derivative of the integral, you just get back to f. When you take the integral of the derivative, you get the original function, but that whole plus c thing comes into picture, and that's sort of what's going on here. We'll go into more detail with that when the time comes, but another thing we can say is that if the velocity v of t is continuous on a to b, then the integral from a to b of v of t dt is equal to, it's going to be s of b minus s of a, okay, or s of t is the position And this, S of B minus S of A, this is just the displacement. Right? This is actually the definition of displacement from A to B. Okay, so the displacement on A to B. That is the definition. Displacement is just S of B minus S of A. All right, simple as that. Okay, so let's take a look at an example dealing with this, and actually we'll look at a couple examples. Okay, so we will start simply. Let's look at the definite integral of x squared dx. Okay, now what this thing actually does for us, 0 to 1 of x squared, right? Well, x squared looks like this. Okay, and the integral is going to give us, right, the area beneath the curve, or between the curve and the x-axis. Okay, so that's what the integral gives us, if you remember. Okay, now this is something before we would have had to use a bunch of rectangles to try and approximate this. I have no idea what it is. I know it's got to be less than 1, and it's probably less than a half too, because a half would be this triangle here. Okay, so I know it's between a half and it's got to be greater than 0, but other than that, I have no idea what that area might be. Well, we can use the Fundamental Theorem of Calculus to figure this out. So, I'll say by the Fundamental Theorem of Calculus, which I shorthand to FTC, the definite integral from 0 to 1 of x squared dx is going to be capital F of 1 minus capital F of 0, where capital F of x is any antiderivative of x squared. So what's the antiderivative of x squared? Well, since we can pick any one, capital F of x is going to be 1/3 x cubed. Right? Note, I'm not doing plus c, I'm just picking an antiderivative, not the antiderivative. That's the distinction. Okay, so what we get is that the definite integral from 0 to 1 of x squared dx is, all right, I'm going to plug 1 in, so that will be 1/3 times 1 cubed, minus, and I'm going to plug 0 in to capital F, 1/3 times 0 cubed. Okay, so this simplifies out to be 1/3. Right, so that area here is actually 1/3. Okay. So have you ever wondered, like, where, if you look up the areas of, really crazy shapes in a book somewhere, and you ever wondered how they got the areas? I mean, you can figure out on your own, like, where they get rectangles and circles and stuff. I mean, that's not too hard to figure out, especially triangles, all that. But something strange like this, have you ever wondered how they found the areas of things like that? Well, they're using calculus, they're using integration. Okay, now you might think, well, how do we actually know that this is right? I mean, it satisfies what we wanted. I mean, it's less than a half. But let's integrate using the Fundamental Theorem of Calculus something where we actually know the area, something that we know what we should get out. And I submit that we do the triangle that we just talked about. All right, this triangle here will give us an area of 1/2, and that triangle going from the point 0, 0 to the point 1, 1, that, and I'll do it in red just to set them apart, that's the line y equals x. Okay? So to verify, and that's kind of off there, that's y equals x. So to verify, right, consider this integral, the integral from 0 to 1 of x dx. Now, by the fundamental theorem of calculus, right, I know that this is going to be capital F of 1 minus capital F of 0, and here this is where f, not to be confused by the f's up here, so this is going to be f of 1 minus f of 0, where capital F of x is an antiderivative of x. So the antiderivative of x is x squared over 2 plus c, but we're only picking 1. No, I'm using the capital F here, not the integration sign. So this is going to be 1/2 x squared that we're going to choose. Okay, so from here, the integral from 0 to 1 of x dx is going to be, I'm going to plug in 1, so it'll be 1/2 times 1 squared, minus, now I'm going to plug in 0, so that should be 1/2 0 squared, and so we end up getting 1/2, which is exactly what we expected from this triangle here. Right, this red triangle, I know that that area is 1/2. And you could try it with the square as well. Try it with the square. This is the line y equals 1. So you try the integral, or definite integral, from 0 to 1 of 1, and you will get out 1. Okay, so it will work for all the normal areas that we know how to do. Okay? All right, from here, before we start doing any more examples, what I want to do is sort of introduce a notation that will save us some time, because I don't want to have to keep writing things like this. It's kind of awkward to write things the way they are. What we're going to do is introduce a notation that will help us just write it all out and from line to line instead of having to write any text. So here's basically the notation we're going to utilize. Okay. So basically, if I have the definite integral from a to b of little f of x dx, okay, what I'm going to write is this is going to be capital F of x with a bar from a to b. And what the bar means is that I'm going to evaluate capital F at b, capital F at a, and then subtract. So if I were just to tell you, all right, let's do x squared bar, I don't know, let's do 2 and 3. What this would be 3 squared minus 2 squared. Okay, so that would end up being 9 minus 4, which is 5. Okay, if I had, say, x squared plus 2x, and I was going from 1 to 2, now this you have to be very careful about, because I'm going to plug in 2, so 2 squared plus 2 times 2. Now I always put brackets around everything just so I'm very careful. Minus, now I'm going to plug in 1. So it would be 1 squared plus 2 times 1. Okay. So this will be 4 plus 4, so that's 8. Minus, this is 1 plus 2, so that's 3. Okay, so that's going to end up being 5. again, that was actually not planned. Okay, so that's what this notation is. And so essentially on the last example, when I had the integral from 0 to 1 of x squared, what I would do instead, and this will just simplify the way we write this out, the integral from 0 to 1 of x squared dx, I can instead just go straight to an antiderivative. So the antiderivative, or an antiderivative of x squared, is 1/3 x cubed, and I could just put 0 to 1 instead of having to like break and find a capital F and then write it with f of 1 minus f of 0, and then it's just 1/3 the 1 plugged in minus 1/3 with the 0 cubed plugged in, so I get 1/3 out again. Now before you ask, I get this question a lot, well, why don't we put the plus c in? Okay, and we don't put the plus c in definite integrals because it's pointless. Now I'll show you why in just a second. But basically, the plus c is for antiderivatives. It's for indefinite integrals. Indefinite integrals, you have an infinite number of possibilities for your indefinite integrals, right? The actual antiderivative of x squared is 1/3 x cubed plus any constant you might ever want. Plus 1, plus 2, minus 10, all the constants. Okay? We don't do it for definite integrals because if we did, let's say I did that. Let's say I said, all right, 1/3 x cubed plus c, and I'm going to evaluate that from 0 to 1. Well, that would be 1/3 times 1 cubed plus c, then minus 1/3 times 0 cubed plus c. And what we would end up getting here, well, that's 1/3 plus c. And this is, when I distribute that negative, just minus c. The c's cancel, and I get 1/3. That's going to happen no matter which constant you pick. If you did plus 10, you'd get the same thing. So it's going to cancel every single time, right? So there's no need. And if you look at the actual statement of the Fundamental Theorem of Calculus, it says any antiderivative. You only need to find one. And since you can use any antiderivative and still get the right answer, so you might as well use the one where c is equal to 0. So let me write that. Okay, so also because we might as well use the antiderivative where c equals 0. Since we can use any antiderivative, we might as well use the easiest one there is, where c is 0. Okay. All right, let's start looking at some more examples. Okay, so here we're going to look at the definite integral from 0 to 1 of 6x minus 6x squared dx. All right. Again, we're keeping this pretty simple to start with. Well, first, if we're doing a definite integral, we still need to find the integral of 6x minus 6x squared. So this is going to be 6x squared over 2, right? That's the antiderivative of x, all right? Minus, okay, it will be 6, remember those constants come along for the ride, times 6 cubed over 3. And I'm going to evaluate this from 0 to 1. Now, the problem a lot of people seem to be having is once you integrate, the integral sign disappears but is replaced with this bar. Now, when you start to simplify, because we will want to simplify this first. I guess you don't have to, but we're going to. you keep the bar, and the bar stays until you do the difference. Okay? So, I'm going to simplify this, right? The 2 goes into the 6, as does the 3. So this is going to be 3x squared minus 2x cubed, and we're going to evaluate it from 0 to 1. So the biggest problem I see people having with this is not distributing the negative signs right and not doing it in the right order. The top goes first. That should sound familiar, right? The top goes first. So this is going to be 3 times 1 squared minus 2 times 1 cubed. All right, so here I've plugged in 1. I'm going to subtract, plugging in 0. Now here it's not going to matter much, but often people forget to put brackets around this and it screws everything up and you get the wrong answer. So always, 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 always put this second piece in brackets. Was that enough always to get my point across? Okay, if not, always. So this is going to be, well, 3 minus 2, so that's just 1, minus, that's just 0. So the whole thing comes out to be 1. Okay? Well, there we go. Now, this function itself, 6x minus 6x squared, you could factor out a 6x and you'd have a 1 minus x, right? This guy looks something like this. Okay. Oh, you can't see that. All right, it looks something like this, and we just found that whatever this area is here is 1. Okay. So hopefully you're starting to see what a powerful tool integration is. We can find the area of just about anything. If we can get a function that gives us this shape, we can find the area. Now you might not think that that's important, but for engineering prospects, that's super important. That can tell you how much of that material you might need to make a strip or a flat piece of whatever in that shape. Okay, that's huge. All right, so this, I mean, may be one of the most important topics in this class, other than the physics stuff from derivatives. Okay. All right, let's move on to another example. Okay, ramping up the difficulty a little bit. Here we go. The definite integral from pi over 6 to pi over 3 sine of 3 theta d theta. Okay, so sine is trig is once again rearing its not so ugly head. But basically we're just going to approach this like we would anything. I just need an antiderivative of sine of 3 theta. So what's the antiderivative of sine of 3 theta? Well, it is of course negative cosine of 3 theta, but remember you need that 1/3. So it's negative 1/3 cosine of 3 theta, and I'm going to evaluate it from pi over 6 to pi over 3. Okay. So now it's going to be, again, I like to put everything in brackets just so I keep everything careful. This is where a lot of people make a lot of mistakes, and students don't trust me or believe me when I say that. They don't want to do what I say, but I've seen this enough times to know that if you keep everything in brackets, you'll be fine. So anyway, I'm going to plug in pi over 3 into cosine, or cosine of 3 theta. And then this minus sign, and this piece I'm going to plug in pi over 6. And again, this is still negative, okay, cosine of 3 times pi over 6. Okay, so this is going to be negative 1/3 cosine of pi, okay, minus a negative 1/3, so that will become a plus 1/3 cosine of pi over 2. Right? So cosine of pi over 2 right off the bat, that's 0. Cosine of pi is negative 1, so this is negative 1/3 times negative 1, so this is 1/3. Okay. Again, be very careful with how you do all this. One thing that I see some people do, and you'll see me do this as well, is when they get to here, often I will factor out that negative 1/3. So I will say negative 1/3, then I'll plug in all my stuff. So it will be cosine of 3 times pi over 3 minus cosine of 3 times pi over 6. And that just keeps it, you know, you can factor out the negative so you're not having to worry. It's always still just this thing minus this thing. You know, it's however you want to do it, because then, you know, you get down to cosine, this is cosine of pi minus cosine of pi over 2. All right, and so that ends up being negative 1/3 times negative 1 minus 0. So that ends up being 1/3. So I think this looks a lot cleaner than what we had here. Okay, but there are still cases where you might actually have to end up putting these in brackets because there's sums and stuff. So sometimes it doesn't work that way, but often you could maybe factor things out and just kind of leave that. You just have to make sure you actually do leave it out front. All right, next example, the definite integral from 1/2 to 4 of 1 minus 1 over x squared. So first thing we're probably going to want to do here is simplify. So I'm going to simplify this guy to be the definite integral from 1/2 to 4 of 1 minus x to the negative 2 dx. All right, so now we just need to take the antiderivative and then evaluate it at 4 and 1/2. So the antiderivative of 1 is simply x, and then x to the negative 2 will be x to the negative 1 over negative 1. And we're going to evaluate this from 1/2 to 4. All right, and let's simplify this a bit. As you see, I just did the thing verbatim. I didn't really you know, mess with simplifying it that much. But basically, this is going to be x plus 1 over x when I move that back down. All right, so it'll be 1/2 to 4. All right, so now we're going to plug things in. I'm going to plug in that 4. So it'll be 4 plus 1/4. And then I'm going to subtract, plugging in 1/2. So it's going to be 1/2 plus 1 over 1/2. And again, a lot of you probably would not write this step. Many of you might actually go straight to 4 plus 1/4 minus 1/2. And this, actually, let me get the brackets there. This is just going to be plus 2. Okay, so it's going to be 4 plus 1/4 minus 1/2 minus 2. Yes, that negative sign has to distribute. Okay. All right, so this is going to be basically 2 plus 1/4 minus 1/2. So 1/2 is 2/4. So this is going to end up being 2 minus 1/4. Right, and 2, okay, is 8/4. I'll go ahead and write that out. It's 8/4 minus a fourth. So that'll be 7/4. All right. And that's pretty much that. Okay, you just integrate, plug in the values, be very careful about how you do so, and there you go. All right. Next up, let's look at the definite integral from 2 to 4 of 6 over x dx. Okay. So, remember, this 6 over x is a very special rule. Don't try to use the power rule on that one. That's your natural log. So this is 6 times 1 over x, essentially. So this is going to be 6 natural log of the absolute value of x. Okay, we're going to evaluate this from 2 to 4. All right, so this is going to be 6 natural log of the absolute value of 4 minus 6 natural log of the absolute value of 2. All right, and I would say you could leave it like this, but if you were to check your answer in the back, or you were to put this answer on MyLabs Plus, it would probably count it wrong. You probably wouldn't see this form of the answer in the book. Here's what you would do to simplify this. You'd factor out that 6, and then you'd have natural log of 4 minus the natural log of 2. Okay. So the natural log of 4 minus natural log of 2, well, remember, we can split up division within a natural log using subtraction, so we can bring that back together with division here. So the natural log of 4 minus the natural log of 2 is actually the natural log of 4 over 2. So this is actually just going to be 6 natural log of 2 is the final answer. Wow. Give you a second to pour that over. But one thing to really remember here is you've got to do absolute value in your ln, because if you have negative limits of integration, the only way this is going to work is if you put those absolute value bars. Okay? All right. Next up, integral from 1 to 4 of x minus 2 over the square root of x. So much like when we first started learning derivatives and when you first started doing antiderivatives and yada yada yada, this should seem very similar to all this. We have to simplify this before we can get going. We don't have a quotient rule for integrals yet. Okay, so we've actually got to simplify this down a little bit. And we do that by splitting up the fraction. Okay, so that's just going to be the integral from 1 to 4. As you see, of course, I'm writing the integral sign again. It's x over the square root of x minus 2 over the square root of x dx. All right, so this is going to be the integral from 1 to 4 of, all right, this is x to the 1 over x to the 1/2. Or if you divide a square root out of x, you're just going to end up with a square root of x. So this is x to the 1/2. And this is minus 2x to the negative 1/2 dx. This is something some of you are still messing up. A couple students are still messing this up. I'll tell you, if you don't get these exponent rules down, you're going to have a really tough time finishing off this class. And if you're going on to Calc 2, you're also going to have a tough time. Okay. All right, so now we can just integrate and start evaluating. Right? So the integral of x to the 1/2, well, that's going to be, if you remember, we find what the exponent is going to be. So it's 1/2 plus 1, which is 3/2, and then this constant outside is just the reciprocal, just 2/3. Okay, then this will be minus 2 times, so x to the negative 1/2 plus 1/2, that's going to be x to the positive 1/2, then we multiply by the reciprocal, which is 2. And I'll go ahead and write it like this so you see what's going on. It's 2 over 1. Okay, and we're going to evaluate this from 1 to 4. All right, so simplifying this is, of course, 2/3 x to the 3/2 minus 4x to the 1/2 evaluated from 1 to 4. Now that 1 isn't going to be much of a problem, but that 4 may be. So here we go. I'm going to plug in 4. So this is going to be 2/3 4 to the 3/2 minus 4 times 4 to the 1/2. Right? And minus, now I'm going to plug in 1, so it's going to be 2/3 1 to the 3/2 minus 4 times 1 to the 1/2. So this piece is not actually going to be all that bad. This piece may give some of you some trouble. So here we go. This is 2/3. Now, some of you don't remember how to do this, but basically what you can do is say that this is 4 to the 1/2 cubed. Right? And what's 4 to the 1/2? Well, that's the square root of 4, so that's just going to be 2. So this ends up being 2 cubed. All right? And these are just 1s, so I'll just leave that as is. And the rest of this is just kind of cranking this out. Right? So this is 2/3 times 2 cubed minus 8 minus 2/3 minus 4. Okay. All right, so I don't want to waste much more time on just arithmetic, so I'll skip to the answer here, but see if you can get the same answer just going through this. All right, when it's all said and done, we get that this thing is equal to 2/3. Now, can you do this in your work? Just kind of jump to what the answer is? Absolutely. What do you think I'm grading you on? I'm grading you on this, getting to the, well, first simplifying and writing things correctly, getting the integral, and then setting this part up right. The plugging in 4 minus plugging in 1, making sure you actually have that in parentheses the way you need to. From here, I assume you all know how to do arithmetic. Really, don't let me down on that part. Okay, you all know how to do that. All right, and if you don't, I mean, you at least know how to work a calculator. Okay. All right, let's move on to the next example. All right, next example, let's say we have the definite integral from 0 to pi over 3 of secant x tangent x dx. Okay. So what's the antiderivative of secant x tangent x? Well, I hope you all said secant x. You should definitely know that. We're going to evaluate that from 0 to pi over 3. So this is going to be secant pi over 3 minus secant of 0. Okay. Now these you should probably know, but let's say you didn't. Okay. And if you didn't, hopefully you know that secant is just 1 over cosine. All right, so 1 over cosine of pi over 3 minus 1 over cosine of 0. So cosine of pi over 3 is 1/2, and cosine of 0 is 1. So what we basically have here is 2 minus 1, which is 1. Okay. So even if you don't know right off the top of your head what secant of pi over 3 is, you can find it just using what you know about cosine and sine and whatnot. Right? So here's one that probably looked really tough to begin with, but actually ended up being very simple when we got down to it. A lot of these are like that. Okay, so just because you see trig, don't just shut your brain off and move on to the next problem. Just take a deep breath and tackle it. All right, let's take a look at another trig one. Let's focuses. Let's take a look at the integral of pi over 4 to pi over 2 of cosecant squared, or theta d theta. All right, so what's the antiderivative of cosecant squared theta? hopefully you said negative cotangent theta. Okay, so we're going to do negative cotangent theta from pi over 4 to pi over 2. So this is going to be, I'm going to put this in brackets just to, make sure we get this right. This is negative cotangent of pi over 2, okay, minus a negative cotangent of pi over 4. Right? The negative cotangent of pi over 2 is 0. How do I know that? Because this is cosine over sine. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Minus, and this is, well, cotangent of pi over 4 is 1. So this is negative 1. So the whole thing comes out to be 1. And once again, a trig integral that does not end up being all that difficult to do. Okay. Here's another example. Let's say we're looking at the integral from 1 to 2. Let me rewrite this so it's a little more clear. Of z squared plus 4 all over z. So once again, this is very much like what we looked at last time, or a couple examples ago. We're actually going to have to simplify this. This is the integral from 1 to 2 of z squared over z plus 4 over z dz. Okay, so this will be the integral from 1 to 2 of z plus 4 over z dz. All right. So when we integrate that, and notice I rewrote all this notation every time I did this. This is going to be 1/2 z squared. Okay, plus, now what does a 4 over z give us? It's going to give us 4 natural log of the absolute value of z. We're going to evaluate that from 1 to 2. So this is going to be, now I'm going to evaluate this at 2. So this is going to be 1/2 2 squared plus 4 times the natural log of 2. I'm going to go ahead and drop that absolute value bar right now, but you do need it in this piece. Okay, minus 1/2 times 1 squared plus 4 times the natural log of 1. Okay. So this is 1/2 times 4, so that's 2. I'll drop the brackets for now. So that's 2 plus 4 natural log of 2. Okay. Minus 1/2 plus, well, the natural log of 1 is 0. So this is just going to be minus 1/2. Okay. So that's 4/2. So this is 3/2 plus 4 natural log of 2. And we can leave our answer like that, or often what people will do is move this up here if they want, but I think it's fine just the way it is. Okay. All right, one last thing I want to show before we finish this off is what we talked about last time about symmetry can really help us here. I know that this is an even function. Okay, so this is even, meaning that the integral from -2 to 2 of this even function is the same thing as 2 times 0 to 2 of this integral. Okay. And so what happens here is this actually simplifies the problem a lot, because this is 2 now times the integral will be, of course, 1/3 x cubed minus x. And you see how I made the parentheses and the bar? That's our grouping symbol. Okay, and then all I've got to do here is plug in 2, because this will be 1/3 times 2 cubed minus 2. All right. Then, oops, let me go ahead and put brackets around this. Minus 1/3 0 cubed minus 0. Right, and this whole thing just becomes 0, so this ends up just being 2 times, this is going to be 8 cubed minus, or sorry, not 8 cubed, 8 over 3, 8 thirds minus 2. And this is 6 thirds, so this ends up being 2 times 2 thirds, so we get 4 thirds out. Okay. If we had just done this the longer way, negative 2 to 2 of x squared minus 1 dx, I mean, we'd get the same integral. Okay, but we would actually have to, we'd actually have to plug in 2, so it'd be 1/3 2 cubed minus 2, and negative 2. And this computation is actually a lot more complicated than this one, because when you're plugging a 0 to this thing, this whole thing just goes away, because really you're just plugging in 2 now and multiplying it by 2. Whereas, you know, here, this is a much more complex computation. I will let you do this on your own to see if you get 4 thirds as well. So that's how it helps with even functions. You'll see me do that every so often. When I notice that a function is even, I will set that up. And if a function is odd, like I know just right off the bat that the integral from negative 1 to 1 of x cubed dx is 0. Well, you know, how do I know that? Because this guy is odd. And if you want to prove it or go through it, the integral of x cubed is 1/4 x to the 4th, and we're going to evaluate it at negative 1 and 1. So we'll plug in 1, and then we'll plug in negative 1. Okay, and we end up getting a 4th minus a 4th, which is 0. So knowing and being able to identify odd functions saves you a lot of time, because I know that this is just 0 because it's odd. Okay? Alright, so I think that's enough examples for you all to get started on the homework, and it should be enough for you to get started on your worksheets. Again, I say there are way too many examples out there for me to do it, you know, enough of them. Okay? But these basic integral rules you really need to practice, because once we move on to 5.5, you'll be going a little out of order, but once we do that, you need to have these basic rules down really well, because 5.5, our next section, is going to be the reverse chain rule. So if you don't have this stuff down really well, specifically 4.8 and 5.3, okay, you're going to have a really hard time in 5.5. Okay, so make sure you have all the basic rules down extremely well. It's going to remind you of when we moved from the basic derivative rules to the chain rule. Okay, so make sure you actually have that down extremely well. Okay? All right, and I will talk to you then. Cheers.